You have analyzed FeSem. You take take the sample, and operator generally does so. Okay. Briefly, what Ron has covered in the morning. So this is the electron column. On the top of the column, we have the emitter. So field emission, Schottky field emitter we have. After that, the lenses, series of lenses, condenser, objective. We have scanning coils also, because it is a scanning electron microscope. There will be scanning coils, and as Ron explained, there are several detectors. So there is one thing you remember he was mentioning about the VP mode. VP mode. So for VP mode, that is low vacuum, there is one detector also present over there. That one actually not.
Yeah.
That one. Yeah. That one is the PPS. Yeah. And this is actually the chamber. This part is actually the chamber where we inserted our sample. So from the electron Fe gun to the chamber, it is under complete vacuum, high vacuum, and to maintain the vacuum, in any system, FeSem, generally three types of pumps are given. Generally, one is rotary pump, which is outside the electron column. One is TMP, which is below the electron column. Actually, it is here TMP, and on the to maintain the vacuum level in the field emission gun, we have the ion gun pump, which is known as ion gator pump also.
What is the order of vacuum?
Yeah, so 10 to the 1 minus 4 Pascal, 3 to 4 Pascal is the chamber vacuum, and in the gun we have the 10 to the minus 7 Pascal. Okay, so tentatively here you can see that vacuum level. So if you gun system vacuum 10 to the minus 6 millibar, 10 to the minus 6 millibar, so 10 to the minus 4 Pascal basically. 10 to the minus 6 millibar means 10 to the minus 4 Pascal, and here 10 to the minus 9 millibar, so 10 to the minus 7 Pascal. So this is the tentative level of vacuum. You can see this particular system vacuum, that is chamber vacuum, can go up to 10 to the minus 7. If you even keep the system overnight, you do not use the system, after maybe 5-6 hours, 10 hours, the vacuum level even increases a bit. So this is the vacuum level. Any idea why vacuum is required in electron microscope?
To avoid attenuation of vacuum.
Yeah. Oh, because to
increase the mean free.
right, yeah. So so her answer was to decrease the mean free path basically. Sorry, to increase the mean free path. What actually her meaning is? So we are the electron is coming. So if it is not under vacuum, the electron will scatter. It will not reach to the sample at all. So that is why the vacuum pumps are given. So we have this nitrogen gas cylinder which is used for the venting the chamber, because it is under high vacuum. To exchange the samples, the nitrogen will be given. Air can also be given here using the air compression. Okay. Here actually two samples we have already inserted. So right now I am not opening the chamber because it will again take away 5 to 10 minutes actually. And this is your the sample holder. This is your stage. Okay. So this is actually basically your stage. Maybe after everything is over, by maybe tomorrow also, if you are there tomorrow during sample exchange, sometimes you can get to see the or otherwise I will just show you. This is the sample, basically the stage, some part of the stage, not the total stage actually you can see, and the total sample holder that you can see, and the stage can be controlled by this. This is called joystick. So 5 control X, Y, Z, rotation and tilt. These 5 controls that you can give to your stage. Okay. Okay, so now this is basically the software by which we do our work. We control the parameters, several parameters. So this is actually the control panel, and this is the screen where we can see. This is actually the CCTV image. Right now, what we are saying is basically nothing but the camera image. Camera image. You can go here. You are quite tall. You can see this image is. This particular image is actually not the electron image, it's a camera image, and you can choose which detector you want to use basically. So secondary electron detector, variable pressure secondary electron detector, backscattered electron detector, annular stem detector, in lens detector. So these 5 detectors are available in your system basically. And these are the control where you can control the electron beam. Now the EST is actually off, so we can switch on the EST. Okay, so before switching on the EST, you can just check for your inconvenience this vacuum level and the gun. These two things are tick, green. This will be.
If they are not, then what?
Then you cannot even switch on the EST.
Okay.
EST means the your
The gun.
gun. Basically, you are giving acceleration to the electron. Basically, that's the EST. Okay. If these two things are not tick, you cannot even switch on the EST. After switching on the EST, you can change the kV from here, okay, or from here. From here. If you cannot see, you can come up. There are plenty of places you can see the screen. If you can come here. This is the working distance. So you remember on explaining that working distance, by changing the working distance, you can control the level of signals that you are actually acquiring, and the working distance plays an important role. So basically, when you are depending on the detector that you are choosing, you have to change your working distance accordingly, and also indirectly the sample actually controls the WD. Depending on your sample, you have to change your accelerating voltage, and accordingly you change your WD. You understand that particular thing, because that is the one of the key things that you as a researcher need to understand for your sample analysis. So it is what are the 3 things? WD, accelerating voltage, and the probe current. Am I correct?
Yes.
Yeah. So okay, again, to control the probe current, there are 6 apertures available in this particular system. It could vary depending on the manufacturer and also depending on the sample that you system that you choose. So here for a standard application, we generally use the 30 micron. You can for lower kV applications, suppose biological samples, so lower kV applications where you do not need too much of probe current, you can use the further below 20 or 10. Please remember, the lower the aperture, number of electrons that is actually passing through the system is very low. So you need to optimize which particular aperture you need to use
According to our sample.
Yeah. So 30 is the ideal. You can go below that. Preferably, other than EDS EBSD, we cannot go beyond 30. For EDS EBSD, sometimes we can choose the 60. Well, yeah, you choose any other aperture for your EBSD application, or still 30 you are using? 60. So see here, for EBSD, since you need large amount of extra signals, actually for EDS large amount of extra signals, a large amount of signals basically, the difference. So you need to use a bigger aperture. So large number of electron is actually should flow and hit the your sample. So that is the idea of the aperture. Okay. So these are the 2 modes available, HV and VP. As you can see, VP stands for variable pressure. So biology guys, you can use the VP mode here. I mean, you can come here and ask that, since your sample, when do you use the VP? Anyone? Not you. Or anyone use the VP? Not you. I mean, anyway. VP कब यूज़ करते हैं? VP आज सुबह बोला है राम ने। VP कब या लो वैक्यूम कब यूज़ करेंगे हम लोग? जब हमारे सैंपल में वाटर कंटेंट होगा या बीम सेंसिटिव होगा, ठीक है। Why we are using or how we are using? So VP's mode introduces the nitrogen into the system up to a certain level. Our system level is 60 Pascal. So we introduce nitrogen molecule. Now what happened? The electron, after it crosses, this is actually the last part of the pole piece, last part of the electron column. Are you getting me?
Yes.
Whatever, and please do not forget to ask questions if any confusion. So this is the last part of the electron beam. So just after it crosses the last part of the electron column. I'm sorry. So when it crosses the electron column, what it will feel actually? What it will encounter? It will encounter a lot of nitrogen. Right. So it will not directly hit the sample. It will scatter a little bit, not up to too much that it will not electron actually does not so it will scatter a little bit and reach to the sample. So sample which is little bit hydrated, little bit in a beam sensitive samples will not be that much affected.
What is the amount of nitrogen flow? Like
Yeah,
50
not-
ml per?
No. Nitrogen flow, that I do not know, but the level of vacuum is 60, up to 60, 10 to 60. You want to include anything? You can, yeah. So, his question is there any measurement of the nitrogen flow into the system or?
They're supposed to be like that. Yeah.
Okay.
For
Okay.
us, as long as you monitor the pressure, then
Yeah. As long as you actually basically control the pressure of the vacuum level basically. Vacuum level, we are actually seeing what we are actually seeing here. This vacuum level, system vacuum, which is nothing but the chamber vacuum. Now it will show us 10 up to 10 to 60 Pascal, 10, 11, 12, up to the step size of 1 Pascal, we can change. And for that particular VP mode, we can use our VPAC. Our normal secondary electron detector will not work here. Because why it will not? Because there are lots of nitrogen, and the signal which secondary electrons which is coming to the system, it cannot be detected our normal AC detector. So another separate detector is particularly given, and BSD detector we can work in VP and HV both the modes. You can also ask questions if you feel. Okay, you don't worry. So this is actually the stage specific, stage data, that XYZ rotation and tilt basically. Vacuum is gone.
We can change manually from here after putting these values in.
Yes,
to see what-
yes.
And along with this.
Yes. Preferably when you are moving the stage, you should be in that particular mode. That mode means this mode is actually camera mode.
Okay.
Camera mode. We are basically seeing the camera, not the any electron signals. It's optics actually basically. Light. So by just clicking here, this is the option that is generally given to change the from the
Camera
electrons to camera basically. So camera mode even go. So these are the things. Now I can go to the imaging. Just I'll try to show how the imaging can be done. Just a preliminary few things so that you can be aware. So 5 kV is okay for me, I suppose, and we can choose. So you can disperse it as per your wish.
Sir,
Then
the sample is biological.
no, it's not biological.
What is it?
Okay, just 1 second. Thanks for raising this. I will show you what is the sample. So it's an oxide sample.
Yes.
Right, it's oxide sample.
For the beam sensitive sample.
Yeah, so for the beam sensitive samples,
Yes, yes, I think I should.
preferably preferably we go for the lower KV. Now, how low we should go really depends on the nature of the sample.
So variable pressure has some advantage over there. Means if you lower the accelerating, then you are still doing the same.
So basically we have to optimize. I understand your question. So basically we have to optimize because the peak in the variable pressure mode, since we introduce the nitrogen and the electron signal that is actually coming up actually to the detector is a bit lower than the HV, because electrons are also which are generated are also facing challenges to coming to the detector basically. So basically that we have to optimize, that we can increase a little bit, not a very big difference as in comparison to the HV system. So actually this is basically the sample, and here by using this joystick we can just move the region of interest. I know everybody may not be able to see the screen, but everybody get a chance to operate the equipment. Any questions, come up with those actually right now if you have any queries. Okay. So right now we are at a very lower magnification, and actually previously, so when you are inserting first in your samples, you'll get something like this. I mean, maybe. So your stage is actually will be very low.
Okay.
Now your WT may not actually giving you the correct data. Now it is giving the correct data because it has already been focused.
Okay.
So I will let's defocus everything. Okay. WT is gone. Now we will go to the secondary electron. Okay. We'll select the AC2 signals and we try to focus it. This is the you understand? This
Yes.
is the way we do the focusing. We do the brightness contrast, and we again change the magnification and try to see what is in there. Now this part it's bit agglomerated. Although he has given, I mean these are sample prepared by Ron. You see, you cannot even see the, if I'll show you the sample naked eye, you cannot see the any particle over there, but still you can see the level of agglomeration. So but actually what I am trying to say, your sample preparation is bit critical. The better more time you spend, the better
in the sample.
So I am trying to get some region where distribution is more or less good. Okay. So you can see the few particles are there, and more or less it is distributed evenly. Now the working distance is too large. Now I am trying to reduce the working distance by using the joystick.
Okay. What are those plus minus buttons, sir?
Scan speed.
Sorry?
Scan speed.
Scan speed. So when we are actually observing the image, you can go for a higher scan, basically speed scan. I mean the speed can be higher. But when you are taking the final image, your scan speed should be lower actually. As low as possible or as low as it could be. Okay. So these two buttons where we can control the scan speed, and these are the further controls. I mean, you can go for this also. The same thing. This is changing means this is changing.
Okay.
So higher number means the lower speed. Basically, the speed is lower. Higher number means
Lower
the
speed.
the numerator lower speed.
Okay. Okay, got it.
Yeah. So now I will show you the astigmatism correction, how it can be done.
Okay.
How the astigmatism error, why it is generated, and can you recall or something? Why astigmatism error is there?
They have more than one wavelength, and there is second thing is the distance of the thickness of the particular lens used.
Yeah, you're very correct. So basically, the what? So let me just tell you this thing is the interesting thing. So basically, stigmatism corrections occurs due to the imperfection in the electromagnetic coils. These are nothing but the electromagnetic coils, right? So since it has to be electromagnetic because electron wave is the electromagnetic charged particle. So it has to be the electromagnetic coils. There are imperfections in the electromagnetic coils. So that is why the stigmatism error occurs. Other than that, he has mentioned actually another error. Yeah, chromatic aberrations. Why it is occurred? Because we always thought, or we always considered the wavelength of the electron beam is actually a single wavelength, which is not always the
That
case.
is ideal condition.
Sir, sorry.
That is ideal condition.
There is ideally we should get it, but we will never get it. So it will be mixture of the wavelength. So nowadays things are become very, due to the technology development, the chromatic aberrations are now very low in any systems, but especially these JICE systems have better control on the chromatic aberrations. That is how the field emitter are being taken care or are being prepared nowadays. Okay. So here, what I'm trying to say. So this is the the control where we can control the focusing basically. So after we do the focusing, just to control the brightness.
Focusing basically controls the coils, the
Exactly.
current in the coils.
Exactly. So specifically the objective lens.
Okay.
Objective lens. So there are two types of lenses. One is condenser lens. Second one is objective lens. Condenser lens is on the upper part of the electron beam. Objective lens on the lower part of the not electron beam, electron column. So when we change this particular focus, actually objective lens we are controlling. We are controlling the current in the objective lens.
Exactly.
Nice. Actually, these interactions, the more you interact, the more I can, give you some inputs actually. Yeah.
Sir, what are these buttons? Can rotate?
Yeah. So these are bit. I'll
Okay.
come into it. I'll come into it. So here I am actually trying to adjust the brightness contrast so that you can understand the difference I make when I completely actually stigmatism is already been done, but I'll remove the stigmatism and then I will show how it is done. It can be done. So first I will actually destroy the focus. Okay. So the focus and these are the two controls, stigmator X and Y, where there are actually coils are there, stigmatism coils. Two coils are there which we can control. The current we can control, and by using these two particular coils, we actually trying to prevent that particular error. Now everything is gone. Now I try to fix it actually. First thing we will do that we will first try to focus. Now you see these elongated things. See, you cannot be the spherical because the stigmatism, because there are lots of stigmatism error present in this particular image. Now I try to correct the stigmatism. First I'll change the
Why?
here little bit of correction.
So by changing the signature, what is the change?
What is?
What is the change? It's a old.
No, it is actually the these are nothing but the coils yeah. So nothing but the coils, actually stigmatism coils.
EM lenses.
Yeah, electromagnetic lenses, coils basically. So and these are positioned on the final part of the electron column. Now we are how we control in electromagnetic lens? We are actually basically controlling the current which is passes through the coil, and the moment we are changing the current which is passing over coil, we are changing the properties, or you can say path of the electron beam, properties of the electron beam, how it behaves, because we are changing the current. So the electron beam which is passing through this particular coil is also changing its path, its properties, its behavior. Am I understanding how physically you can visualize that particular thing, right? So basically we are changing the current and we are changing the electron beam properties basically. So after we do some stigmatism correction, and what the moment you goes from this elliptical image to the circular one, you can understand that your stigmatism error getting rectified. Okay, after this rectification, finally again you do the focus.
How we will get to know that we have to rotate clockwise or anti-clockwise after seeing that
There is
error?
no yeah. So what is the rule?